So in this video, we're going to introduce the concept of the dot product, which is introduced in your text in section 2.9. So rather than actually show the formulas, I'm just going to I think sometimes it's easier to see this if you just look at an example. So there's two ways to define a dot product. One is kind of based on a linear algebra point of view, and another is based on a geometric point of view. So you might not be surprised that you use the linear algebra kind of interpretation of a dot product when you have a vector decomposed into rectangular form. So I'm just going to, in 3 dimensions, just pick an arbitrary vector in 3 dimensions. I'm going to assign for this vector A an x component of 1, a y component of 3, and a z component of 2. In a similar fashion, I'll just pick arbitrary numbers for vector B. I'll say that it has an x component of 0, a y component of 2, and a z component of 3. Remember that I can compute the dot product of these two vectors by simply taking the like components, say for example the x components, ax is 1, bx is 0. I take the product of those like components, and I add that up for all 3 components. So for y components, the y component of A is 3, the y component of B is 2. I'll take that product, and then I will add that to the like components, the product of the z components, which is just 2 times 3. If I compute those products, you note that I get 0 plus 6 plus 6, which is just 12. And the number is kind of arbitrary because I just picked the actual components of these vectors. But the key thing is just a number. It's a scalar. And that's why this is often called the scalar product as well. So it is very hot in this room. It's Labor Day. It's like 5 o'clock. And if it is a degree under 90 degrees in this room, I would be shocked. SAC has kindly turned off the air conditioning on our day off. So how would I actually go about computing the dot product using the geometric definition? Well, one thing I hope everyone realizes is even though I'm drawing these 2 vectors in a plane, if you have any 2 vectors, which you can kind of prove this to yourself by just taking your hands and hold them in any arbitrary orientation, and assume that these 2 fingers are the vectors, note that there's always some angle that separates the 2 vectors in kind of a planar sense. And we call this vector theta. And notice that naturally there are 2 different angles that kind of describe the separation between them, but by definition we always pick the smaller. And remember that the dot product, another way that you can describe it, from a geometrical perspective, is just the product of the magnitudes times the cosine of that planar angle in between them, theta. Now ask yourself, what does the actual function cos theta look like if it were to be plotted from 0 to 90 degrees? And if you recall back to your trigonometry class, you probably remember that the cosine of 0 is 1, and it varies kind of in a traditional wave-like fashion down to 90 degrees, where the cosine of 90 is 0. So if I write an expression for the dot product of A and B, and I particularly look at the case when theta is equal to 0 degrees, you'll notice in that case it's just the product of the 2 magnitudes. And in a similar fashion, if I take the dot product for the case when theta is equal to 90 degrees, it's just going to be 0. So what's happening there? Well, you notice that these 2 vectors, as they separate and become more and more dissimilar in terms of their orientation to one another, the dot product, the magnitude, reduces. And that's why an interpretation of the dot product is actually a measure of physical alignment. When you take more complicated courses in signal analysis like vibration or engineering analysis, you'll actually see that it's actually more broadly a measure of the similarity between 2 vectors or signals. So just keep those 2 things in mind. Remember that there are 2 definitions for the dot product, a geometric definition along with kind of a linear algebra definition. So why are dot products going to be useful for us from a mechanical analysis point of view? Well, if I have any vector and I want to decompose it into components along a particular axis, or another way to say it is if I want to take that vector and I want to project it onto a particular axis. And the way I show that is by dropping a perpendicular to the axis of interest, which in just this case is the A axis. What we notice is that I can always find the projection of this vector onto this axis by simply taking a dot product of the original vector with a unit vector along that particular direction. So if you notice in this case, not too surprising to us, that if we use the triangle rule, notice that original vector A has a component along A, and it also has a component along a direction that is perpendicular to A in this case. And what we find is that we can write by the triangle rule that the original vector A can be written as a sum of the vector along the axis plus the vector along the perpendicular axis. And what this gives us is a way to compute the vector along the perpendicular axis in case we ever need to do that. So there are some examples in the book that involve this. I don't think I gave you any on the homework, but do be aware of that for potential test questions. So let's look at an actual example of this from the text. Say we were given an expression for a force vector in rectangular components. As we're shown here, this is a force that a cable is actually exerting on a hook. It has an x component of -6, a y component of 9, and a z component of 3, and it's in units of kilonewtons. And say we wanted to, say there was some arbitrary axis drawn from point A to the origin, and we wanted to determine what the planar angle was between the line of action of this force and the actual axis running from A to the origin, along with the magnitude of the projection of F onto the line AO, where AO is denoting from point A to the origin. Well, how would we actually go about doing that? Well, remember that in these problems, whenever you think about trying to find an angle theta, it probably relates back to that dual definition of the dot product that we talked about. Remember that the dot product can be written in two ways. It can be written as kind of this linear algebra approach, A dot B, and it can be written as mag A, mag B, cos theta. And what that says is if we have two arbitrary vectors, as long as we can describe them in rectangular components and we can compute their dot product, and by definition, if we can define them in rectangular components, we can compute their magnitude, I can always find theta is just the inverse cosine of the dot product in rectangular components divided by the product of the magnitudes. So in this case, we just might look at this and say, okay, is there going to be a way that we can write an expression for vector f in rectangular components? Yep, we already got it. Can we write an expression for a vector, position vector from point A to the origin? Yeah, we definitely can. We did that in the earlier example. And then to find the magnitude of the projection of f along the line AO, I'm just going to use this formula that we had here. As long as I can write an expression for a unit vector along the line AO, which I can, if I can write the position vector, I will just take a dot product of that unit vector with the vector in question, which in this case is the force. So if you notice, all of this is going to hinge around a first step of actually coming up with an expression for the position vector from A to the origin. And remember back to the last video, the way that we're going to do that is to write an actual expression for the coordinates of both point A and the origin. So how am I going to get the coordinates of point A? Well, how do I get from the origin to A? Notice that if I were to look at the location of A, it's a little bit hard to see, but in X, I need to step out a positive 1 meter. So the X coordinate of point A is going to be 1. How do I move in Y? Well, I need to move in negative Y. How far do I move? 2 meters. So the Y component will be -2. And once I'm at that point in the XY plane directly beneath point A, how do I move in Z? Well, I move up 2. So the Z component will be 2. So just reviewing the coordinates of A, our X coordinate is 1, our Y coordinate is -2, and our Z coordinate is +2, which we see here. Nice thing about the origin is by definition, all of its coordinates are 0. I can write an expression for the position vector from point A to the origin by simply taking the coordinates of the origin and subtracting away the coordinates of A. Now, if I do that, since it's going to be 0 minus all of the individual coordinates of the point A, all that is going to do is to change, I'm going to create a position vector whose components are simply the opposite of the coordinates of A. So since A had coordinates 1, -2, and 2, the position vector from A to the origin is going to have components -1, +2, and -2. And you can actually show it out if it's easier for you, if that confuses you, but just showing you a little bit of a shortcut. And remember, whenever you have a position vector, you want to check and make sure that the signs are consistent with what you'd expect. In order to move from A to the origin, I need to move back in X in the negative X direction. That is true. I need to move in positive Y. That is true. The Y component of that position vector is positive. And I need to move down in Z, and that makes sense because the Z component of this position vector is negative. Now remember that in order to do that thing involving the inverse cosine that I showed you, you're going to need the magnitude of both the position vector and the force vector. For both of those two things, you calculate their magnitudes by taking the square root of the sum of the squares of the components. Remember, even if the components are negative, when you square them, they will become positive. In addition, remember that when you take magnitudes, even though when you square each of these, for example, in the case of the position vector, will have units of meters squared, when you take square root, you'll get back to the original units of the quantity, which is just meters and kilonewtons respectively. So compute those two magnitudes. From there, since we were given the force in rectangular components and we computed an expression for the position vector in rectangular components, we can take a dot product. Remember that the dot product, in order to compute the number, just take the common components, X components, multiply them together, add on the product of the Y components, add on the components, the product of the Z components, which we're doing here. And notice that will be units of kilonewtons times meter. And then finally, in order to get an expression for theta, remember we need to take the inverse cosine of the ratio of the dot product divided by the magnitude of the individual two vectors. So that's my dot product here in the numerator, 18 kilonewtons times meter. I did that here. In the denominator, I have my magnitude of my force, which is square root of 126, magnitude of my actual position vector, which actually should just be 3 here. It's a little bit of a typo. But if you go back and you make that actual computation, what you will see is that the angle turns out to be 57.7 degrees. So that's an expression for the angle. Now, how would I go about actually computing an expression for the projection of this vector onto this axis? Well, if I have a position vector from A to the origin, I can easily compute what the unit vector is, right? All that I need to do is take and divide by the actual magnitude of that position vector. And from that, just scale by the force. And what you would find is that the projection of the force F onto axis OA is just 6 kilonewtons. So hopefully that was a good refresher of the dot product. And I know when someone's going through examples where they already have the numbers typed, it's a little bit hard to follow, but just feel free to pause as much as you need, and hopefully you'll see that there's not much there. Key points that we covered in the last 2 videos. Make sure if you have an arbitrary geometrical description that you can write an expression for the position vector between 2 points. Be careful with the kind of orientation of your tip and tail. Make sure that you order your coordinates correctly. In addition, know that if you have a position vector, you can always find a unit vector by dividing that position vector by its magnitude. Know the 2 different definitions of the dot product, and know how that you can compute the actual projection of a vector onto an axis by taking the dot product of that vector with a unit vector along that axis.